हेलो हेलो हेलो। Hello and welcome to today's session. I hope my audio and video are visible. Ananta, is my audio visible? I mean, audio audible. Okay, great. So in today's session, in the last session, we had gone through some temperature response functions, and yeah, we had gone to temperature response functions, and we also went through the BioCrew module that makes use of these temperature response functions. So in today's class, like I've already mentioned in the group and in the email, I will be going through some basic concept. What is optimization basically, and what does it mean to optimize parameters or optimize a set of values and such. And this is something that is regularly used when we do crop modeling using measured data and predicted data, not only in crop modeling and a lot of models when we have to validate the model. This optimization is a process that we follow. So basically, what is optimization? Optimization is the process of finding the best solution from a set of possible solutions. So when you solve an equation, uh, say there are multiple equations, you will have several solutions. Finding a lot of solutions and finding the best solution out of it is what is basically the aim of optimization. Now, if you see if we follow real life examples, uh, when you choose a location in the Google Map provides you at times two and three routes. So one route will be the shortest route. So that is obtained through the method of optimization. And what is the shortest route to that location? There will be another route. Another route, the criteria might be that it is not very congested. So the best route would be the other one where it is not the shortest route, but then a lot of congestion can be avoided. So if our requirement is to go to reach a place without a lot of traffic, then we can choose that route in the Google Map. So we have a lot of solutions to, or we have a lot of ways to reach that point, but which out of it is the best of it is what we get through optimization. Similarly, in crops, when we model crops, we need to maximize the yield of a crop by using minimum amount of fertilizers. So how do we maximize the crop yield? And for that, what is the best fertilizers that we can select, or what is the amount of fertilizers that we can apply to get the maximum yield can be done. It's an example for optimization. So we can apply maybe 10 kilo or 10 grams or 20 grams or 30 grams. But applying the say we have three kinds of fertilizers and we don't know which one of it is giving us the best yield. So we'll apply all three of them and we'll get a lot of yield, and out of that, which is the maximum yield that we are receiving is, and which fertilizer it is corresponding to, is something that we can, is something what is basically called optimization. Again, when if you look at a factory, how do you reduce the cost of production? By maximizing the amount of produce that you get. That is optimization. How to maximize the profit, how to minimize water wastage. So maximizing, minimizing, whatever result what we want an optimal solution, means we want the best solution. That is, if our best is to get the maximum out of it, then that is the optimal solution. If our best is to get the minimum result out, or minimize the cost or minimize the loss or any such thing, then that is our optimal solution. So optimization is basically nothing but maximization or minimization. So maximizing, some examples that we can think about is when we want to maximize our profit, when we want to maximize our yield, when we want to maximize the growth of the plant. All these are some optimization by maximizing the result. Then minimizing can be again minimizing the loss, minimizing the minimizing the error, minimizing the amount of fuel that is used, minimizing the cost. All of these are optimal solutions. Optimal solutions that require minimizing whatever is the result that we require. So optimizing is nothing but to get the best solution. The best can be maximum of something or minimum of something. We call that maximization when we want to get a maximum of the result, and minimization when we want to get the minimal of the result. Now, some key components of optimization there are three major components of when we look at an optimization problem. First is the objective function, second is the constraint, and third is the decision variables. The objective function is nothing but the function that requires to be optimized. Now, say if we, I'll go into detail of that. But again, the three components are objective function, constraints, and decision variables. Objective function is the function that requires to be optimized. Constraint is the limit on the solution, and decision variable is the variable that affects the outcome. So let us just go through each one of it one by one. So objective function is what we are trying to optimize, what we are trying to maximize or minimize. So basically it is a mathematical function that we either maximize or minimize. Like in case of profit, we maximize. In case of some cost or error, we minimize. So if you take, for example, a delivery company wants to minimize the cost of the fuel of transporting something by choosing the most efficient speed for their truck. So they want to reduce the cost of fuel that a truck requires by changing the speed of the truck. So that minimizing the fuel cost is what you call as the objective function over here. So if the fuel cost is represented by an equation like this, C of V means C, which is the cost of the fuel, is a function of the speed and is given by this equation. So if the equation is given in this form, this minimizing this C of V will be the objective function. That is, minimizing the cost of the fuel will be the objective function. So what are the constraints in this case? So we now know that for the same example, we know that this is the equation that is relating the cost of the fuel with the speed of the truck. So what does constraint mean in this case? Constraint is some limiting conditions or some conditions with which the speed can vary. Suppose we say that we want to know the most efficient speed at which the cost of the fuel will be less, but the speed limit should not be you shouldn't drive less at a speed less than 40 kilometer per hour, or you should not exceed 80 kilometer per hour. So in that case, if the most efficient speed is 85 kilometer per hour, then it is not a possible solution. And if the speed is say 35 kilometer per hour, then also it is not a possible solution, because the constraint or the condition that we are required to follow in order to find the minimum cost is we have to keep the speed limit between 40 and 80. Again, there can be not just one constraint, there can be a number of constraints. Another constraint is if you're driving if you're driving less than 45 kilometers per hour, then the speed is very slow. Plus, it is also not very safe on the road to travel with a speed less than 45 kilometers. If you're driving with slow speed in the highway, it is going to cause a lot of trouble. So as a result of which, we cannot drive less than 45 kilometers also. So here we have an initial constraint where say the government regulation is you have to drive between 40 and 80. But again, there is another constraint where if you drive below 45 kilometer per hour, then you will not be, it is too slow and it's not a safe speed to travel. And again, there is another constraint where if you drive very slow, say even in 45 kilometer per hour, it will be too slow that you won't be able to reach the place on time. So you have to take care of all these things. You should not go below or above the speed limit. You should not go below the practical speed, as well as you should maintain a speed in such a way that you are going to reach the place in time. So when you say constraints of an objective function, These conditions that need to be met are called the constraints. So in such a case, what can the speed, I mean, what is the limit between which the speed has to stay can be given as the speed has to be greater than or equal to 45, because if you're driving below 45, it is too slow is what they're saying as a practicality constraint. So we will restrict the bottom level or the lower limit of the speed as 45, and they're saying that we cannot exceed 80 kilometer per hour. And here although the time constraint, they're saying you must drive at least 60 kilometer per hour. So sorry, this will be 60 kilometer per hour, not, it should be 60 kilometer per hour or more than 60 kilometer per hour. So in that case, our constraint is going to be the speed. The lower limit of the speed will be 60 and the upper limit should not exceed 80. So this is what you call when we say that this objective function, the constraints have to be so and so when you consider an objective function. So we looked at what objective function is. Objective function is finding the optimal solution to a problem. So optimal can be the maximum or maximizing the whatever requirement you have or minimizing whatever requirement you have. The third component is the decision variable. Decision variable is nothing but what is the variable here that is affecting the objective function. So it is the velocity or the speed of the vehicle that is affecting the objective, affecting the function over here. If you increase the speed, this value of c is going to change. If you decrease the speed, the value of the c is going to change. So what is the function dependent on? What variable is the function dependent on is called the decision variable. So decision variables are the inputs you can change to achieve the best outcome. So if you look at this problem here that is given by this equation, which is the cost of the fuel follows an equation 0.02 v square minus 2v, where v is the speed. Then the objective function over here is to minimize the fuel cost, that is minimize the value of c. Decision variable is the speed v, and constraint is keeping the speed between 60 and 80, not 45 and 80, 60 and 80. So this is what we call as a very general optimization problem. Now, I have an exercise here for you to recognize which is the objective function, the decision variable and constraint. So here this question is there. A farmer wants to maximize the crop yield as a function, crop yield which is given by the letter y or the variable y, and is a function of the water. The equation of the yield is given as minus 0.1 w square plus 6w plus 50. The farm only has 50 liters of water available. So what is going to be the objective function? What is the decision variable and what is the constraint? You can type it in the chat box. Okay, tell me what is the objective function over here from this problem. After reading the problem, what do you think is the objective function over here? No, I mean when you say y, what is it? I mean, is it what do you want to do with y? The answer is correct, y. But what is it that you want to do with y? Do you want to minimize y or maximize y? Y is the yield. In the end, we want to increase the yield. So what will be the objective function over here? Yeah. So maximizing y. Now what is the decision variable over here? Okay. Now what can be the constraint over here? Yeah, if you don't know, just let me know. I'll go to the explanation. But I would like you to try. Yes, very good. So the water should be less than 50 or equal to or less than 50. So when we write a constraint, we have to always make sure that you give it correctly, like as in 50 liters of water is there, so you can either use 50 liters or you should use less than 50 liters. So here the objective function is to maximize the crop yield. The decision variable is the water that is available, and the uh, constraint is that w should, whatever water that has to be provided should be less than or equal to 50 liters. So this is another problem. What is going to be the objective function in this problem? A researcher is wanting to maximize the plant growth by adjusting the amount of nitrogen and phosphorus in the soil. Growth function is given by G, which is a function of nitrogen and phosphorus given by this equation. Here the amount of fertilizer available totally is 50 kg of nitrogen and 50 kg of phosphorus. But applying more than 10 kg of nitrogen directly on the soil is going to be toxic to the plant. Also, applying less than 20 kg of phosphorus will not have any impact on the plant, but applying more than 40 kg will be toxic to the plant. So here, what is the first? Let's go with the objective function. What is the objective function over here? Again, Anamta, you can just say, you can't just tell the variable. You have to say what you're going to do with the variable. Yes. So maximizing G is the objective function. G alone is not the objective function. G is given by a particular equation, but maximizing G is the objective function. Now, what are the decision variables over here? What do you, yes, correct. Amount of N and P are the decision variable because the in the equation, if you change n value, g is going to change. If you change p value also, g is going to change. So amount of n and p are the decision variable. Now what do you think are the constraints over here? So here we have a lot of conditions that are provided. One is the total kg of nitrogen and phosphorus available is given. Another condition for applying nitrogen is given. Condition for applying phosphorus is given. So based on these three information, how can you form the constraint? You will have to form a constraint for n also. You will have to form a constraint for p also. So what will be? Manish, you can also try. Are you able to figure it out, Anamta, or okay. So P should be greater than 20. Okay, then should be less than 10. Okay, somewhat. Okay. Yeah. So here they have said that totally there is only 50 kg of nitrogen, 50 kg of phosphorus. They have also said that 10 kg of nitrogen, more than 10 kg of nitrogen is going to be toxic. So the maximum that you can apply is 10 kg. In case of phosphorus, applying less than 20 kg is of no use. So minimum you need to apply is 20, but maximum you can apply is 40. So in that case, the constraints would be again, objective function is maximizing plant growth. Decision variables are the nitrogen and phosphorus. Constraint would be N should be less than or equal to 10 kg. You cannot exceed 10 kg because it is going to be toxic. So either you can apply 0 or you can apply some amount up to 10 kg equal to 10 kg. You cannot apply anything more than 10 kg. Where in case of phosphorus, there is no point applying less than 20 kg. So it should be either minimum 20 kg or greater than 20 kg, but less than equal to 40 kg or less than 40 kg. So uh, again, your answer will be almost correct, but then you only need to give importance to the equal to, because you can apply 10 kg, but not more than that. So it will be always less than or equal to. Again, in case of phosphorus also, less than or equal to 40 kg and greater than equal to 20. It should be greater than 20 kg. So this is how, this is the general idea of what optimization is. What is an objective function? What are the variables and what are the constraints? So when we won't be going a lot into the detail of, linear, non-linear, and so many types of optimizations are there. And so many types of I mean, this is very linear, very simple algebraic equations where you can manually find it out. But in real world problems, like uh, if you take our BioCro itself, if you take our Farquhar von Cameron model, that model has got three equations, and within that three equations, there are again sub equations. So, suppose you want to find the parameter of that whole set of equation, it is going to be very complicated to solve it manually. So that is why we have codes or we have packages of optimizers that we can use to get certain value, the best optimal values of those parameters, that is going to give the highest photosynthetic rate. Say, for example, if our objective is to maximize the photosynthetic rate, then what parameter is going to give that value can be optimized, can be obtained by optimizing the parameters, say Vmax, Jmax, and TPU rate of the FDCB model. But then we doing it manually is very sophisticated. But basic thing will be to create the objective function, what are the variables and what are the constraints in any optimization problem. Now, something else in optimization that you will, if you go into detail of optimizers, are something called a minima and a maxima. So imagine if you are walking on a hilly road and there are lots of peaks and lots of valleys, like lots of dips are there, lots of peaks are there. A maximum is something where it is like the peak of a hill. You are in a very mountainous terrain, and if you come across a peak, then that peak is called a maximum, and the dip, that is what you see here, this lower point is called a minima. So even when we solve equations, the equations need not always be a straight line, or it need not be a line like uh, the equation need not be a straight line. It can be a line like this, or it can be a line like this. It can take any form. So if the equation is taking a form like this, like what you see over here, then this peaks are called the maximas and the dips are called the minimas. Now, if you see in this whole region, you can see that one maxima is the highest of all. That is the highest peak in this entire graph. And one minima here is the lowest dip or lowest valley in the entire region. This highest value is called the global maxima, and this lowest value is called the global minima. The remaining maximas are called the local maximas, and the remaining minimas are called the local minima. So if this is a graph like this, you can see that this value is the lowest and this value is the highest, and remaining all are low values. But then they are, that is, if you only consider this region, this is a maxima. But if you consider the whole region, this is going to be the highest values of this and this and this and this maximas. So this is what is when you see the term global maxima, global minima, local maxima, local minima means. Now this is only useful to you if you're going to go a little bit deeper into uh, different kinds of optimization methods. Now, this curve is representing the mathematical function or a real world scenario where values are going to change over a range. It can be minimizing cost, profit function. It can be any function. So this can be representing the solutions that every point in this is going to be the velocity, and this is going to be this axis can be the cost. Like we had discussed earlier, say if this is the cost, this y-axis is the cost, and x-axis is v, then all these values can be some v value. It is this value that is going to v value that is going to give, sorry, it is this v value that is going to give us the maximum cost, and this v value that is going to give us the minimum uh, minimum cost. So this entire region is of some values of speed. This entire region is what is the curve that represents. The curve is representing all those values that we can take, and also the cost can vary in between. And this region is called feasible region or search space in optimization. So these two maxima, minima, global maxima and global minima concept can be understood. I mean, required to be understood if you are if you want to go in detail into different types of optimization. Now there are so many types of optimization. So if you want to go in detail into optimization, these terms can be of use to you. Now moving on. when we are running some optimization problems using R, we use majorly two types of packages. One is the Optim package and one is the DOptim package. So today I'll just take you through some concepts in using the Optim package. So say, like usual, we are share this. We're going to open R. You can do it with me, Anamta. It will be helpful. And a new project. Now I want to set the work. This is my working directory. I want to set the directory to my required directory, which is BioPro codes. Now my directory has been set to this. Now what I'm going to do is I'm going to run this same problem. Whatever we had looked here. This cost problem. We are going to do it in R. We are going to find the best solution, best speed. What is the best efficient speed that is going to minimize the cost? So in order to do that, first what we have to do is we have to define the function. Now the function is given by the cost of fuel. Now here the equation that is provided is C is equal to 0.02 V square minus 2V. So that is the function, not the objective function, that function, that is the equation of the cost of fuel. So in order to define an equation, what we have to do, particularly when we are optimizing, what we have to do is we have to use the command function. Now you see here, cost of fuel is a function of the decision variable V. So first we will write that inside the function command. Okay. So we know the cost of the fuel is a function of V. Now, how is this cost of fuel represented in terms of V is what we will define inside here. So for that, what you'll do is you will put a curly bracket and then you will write this equation in here. 0.02 V square minus 2V. 0.02 into V to the power 2 minus 2 into V. So this is the equation that we have been provided over here. Okay, let's put one plus 100 also over here. This equation seems incomplete. Plus 100. So this is the equation that is defining the cost of the fuel in terms of the variable of speed. Now, since we have opened this bracket, we also have to close this bracket. So we'll close it over here. Usually in R, when you open this bracket, you tend to write the function in the next line. It is not going to make any difference. And the bracket will be given in the next line. This is not going to make any difference, but the difference is when you have a lot of equation. Now we know this is just one equation, but you will have a lot of equation within this function. And in such cases, it is better to start the bracket in one line, go to the next line and write all the equations in subsequent lines and then close the bracket at the end. So this is how we will define an equation, any equation. Now here, if it is maximizing the profit, then if profit is given in terms of some currency, then you will write profit here. You will define it as a function of what variable? V, and you will write the equation over here. Now, next what we are going to do is to write the objective function. So here we just have the equation for cost of fuel. Our objective function is to minimize cost of This is our objective function. So we first define the function, and with decision variable v, now we define the objective function. These are all comments just written so that we can recognize what that line of the code is later on. Say suppose we forget and there's a bunch of, there are a lot of codes written. Then it is just writing a comment will help you in recognizing what you're doing. So minimizing the cost of fuel is our objective function. Now, how do we define this? How do we write this objective function in the code is by using this optim optimizer. So optim optimizer is what we are using to minimize the cost of fuel. Now optim is also another function or it's another command. So if you want to see what are the arguments that you require inside optim, then you will do a question mark optim and here everything will come. What is the optim, the command optim, that is the general purpose optimization algorithm. And here you have to give an argument called PAR, the function, method, lower, control, list, and so many things like that. So what is this PAR? PAR is nothing but the initial values for the parameters to be optimized over. So we want to optimize this parameter V. We want to find the best or the most efficient value of this parameter V. And so our PAR is going to be equal to that. PAR is equal to the initial value. We have to give some initial value. We have constraints also, remember. So we have to first give an initial value of P. Say, let's give it 10. Now, next argument is the function. We know the function. We have defined the function over here as the cost of fuel. So function is equal to cost of fuel. Now, now in this optim, when we use this optim for equations like this, in order to apply constraint, this is what we are using now is something where we can't apply constraints. So there are methods where you can apply constraint. So if you see here in this methods, if you go to details, the method BFGS can be used to apply constraint. CG can be used to apply constraint. LBFGS can be used to apply constraint. But if you don't use a by default, Optim is performing minimization. That is, we default method is a method of Nelder and Mead that uses only function values and is robust but slow. So you can't apply any constraint for this method of this method that is utilized in this optimizer. But then you can run various other methods like CG, BFGS, LBFGS, B and all for getting for applying constraints. So first let's see a simple one without applying any constraints. We know that the speed limit and all is a constraint, but let's just see what answer we get without applying any constraint. So here I have defined a function. I have defined the objective function, which is to minimize the cost of fuel. Now, how does Optim know whether it is to minimize or maximize? By default, Optim minimizes. If we need to maximize, we have to put in some other argument that will help this Optim to understand that what you want is to maximize. So by default, it minimizes whatever function that you provide over here, it is going to minimize. If you run this code, run, there's an error. Let's see what the error is. See, there's an extra bracket, so that is why the error came. Now let us run this code. Okay, there's a warning message that says that this is a old optimization is unreliable, use Brent or optimize directly. Okay. So whatever it is just a warning, because this method that is used by default is not very not does not give us a reliable result, because we are not able to apply any constraint. But let's see, just for example sake. So here we are getting that the parameter has to be of value 49, then you will get the value equal to 50. So here they are saying that if the parameter is equal to 49, that is V is equal to 49, then you will get the cost of the fuel equal to 50. So our optimized parameter is 49 and the value of the cost of the fuel will be 50 if the parameter value is 49, which is going to be the minimum cost with an effective speed. Now, how did we get this done? Is something what we look at now. Let us change this value and see. Here we are getting 10. Okay, we get 50. 20, 40, 60, 60, what if we put 10? We're getting 14. Okay, let's put 40 here. All right. Okay. Now, how is this optimizer doing this? Let's solve it manually and see. Now, when we are optimizing any function, like the simple function of cost of fuel, what is happening over here is first you consider this equation. Okay, that is the first thing. Second step is finding the first derivative. So first derivative is nothing but dc by dv. You will find the derivative of c with respect to v. Now, if you know differentiation, when you differentiate this equation, it will become 0.04v minus 2. That is what you get here. So the first step of optimization, what they do is they take the first derivative of this function, and then next what they will do is 0.04v minus 2 is equal to will be equated to 0. They will find out what is the value of v when this whole equation, this first derivative is equal to 0. What will be the value of v? So v is going to be equal to 200 by 4, that is 4 into 50. Okay. Now next step 3 is, we got this. Next step is to find the second derivative. Second derivative is written as dv square. And then when you differentiate this equation, the derivative of the first derivative, then you will get the answer as 0.04. Okay, so that is what 0.04. Now this 0.04 is a value that is greater than 0. So if it is greater than 0, then it means that this is a minimum. So it is saying that at the speed of 50 kilometer per hour, whatever the C value that we are going to get is equal to a minimum value. That is what this that is what is this optimizer is doing. First it is finding the first derivative, then it is equating it to 0. That time you will get the value of v. That v is called the critical point. That is at that point, either the cost is going to be high or cost is going to be low, but we don't know if it is a maxima or a minima. When it is when the second derivative of this part is found out, and if that value is greater than 0, then it becomes a minimum, and if it is less than 0, it becomes a maximum. So if we had got this value as something that is like minus 0.04, then it would mean that at the velocity v, we are getting the cost of petrol is maximizing. It is not minimizing. But since here we are getting the value of 0.04, which is greater than 0, it is a minimum value. So this is what is happening in optimization. If you take a simple problem, they will first find the, if it is one variable. If it is one variable, they'll first find the first derivative equated to 0. Then they will find the critical point. Then they'll find the second derivative. And if it is greater than 0, you know that it is a minima. If it is less than 0, you know that it is a maximum. So this is how a optimizer is finding out the critical point or the V point. Now we got 50. Now if we apply this in this equation, 0.02 into 50 square, basically this equation minus 2 into 50 is giving us this value 50. So that is how this optimizer over here got all these values. If you can see, the parameter value, which is V, critical point is 50, and the cost of the fuel is 50. This, when we solve it manually, is again giving the same answer. So this is how the optimizer is optimizing the function and obtaining the variable, the most efficient value of the variable that will minimize the function, which is our objective function. Now, in the same way, let's do it for the next problem. That is, a farmer is wanting to maximize the crop yield as a function of the water supply. Equation is given by y is equal to minus 0.1 w square plus 6w plus 50, but the farm has only 50 liters of water available. So in the same way, we will again define the function. Define the function, which is basically max yield. Yield is going to be a function of water, and it is given by the equation the minus 0.1 w square minus 0.1 into w square plus 6 into w plus 6 into w plus 50 plus 50. This is the function. Now our objective function is going to be maximize yield, and then using the optim function, our parameter is going to be, initial value of the parameter is going to be say 30. Then the function that is going to be optimized is going to be yield. Now another thing what we want to do here is we want to maximize the yield, but I had told that this function optim by default it does only minimization. So in order to make it into a maximization problem, we will use this argument called control equal to list fn scale equal to -1. Now what is all of this is something we can go to the help and find out. So if you see here, there is something called the control. The control argument is a list that can supply any of the following components. Fn scale, an overall scaling to be applied to the value of the function during optimization. If negative, it turns the problem into a maximization problem. So by default, since it is a minimization problem, by default, if you don't give this, it will find the minimum yield. Required water that has to be supplied for minimum yield, but what we require is to maximize the yield. So in order to make it maximization objective function, we use this control argument, which has to be given in the form of a list with this what do you say, that component fn scale put as -1. So what it is doing is, whatever is the problem, it will maximize it. It will find the negative of it. So this equation, it will write it as negative. So in that case, what we are going to get is going to be the maximized value. So now when we run this and this, again, what happened? Okay, here there is no comma. So such small things can make errors. Okay, so we got the maximize function. Here we have got maximize yield. It is saying that at an initial value of 30, the maximized value is going to be 140. So let's see by solving it manually. Okay, here it is given 500. So let me do this 500. Here also I'll change it to 500. And then I will run this line. I will run this line and you will see that maximize at 30, you are going to get 590. Now, if you try to solve it numerically, the first step is write the function, which is minus 0.1 w square plus 6w plus 500. The first derivative of it is this term will come here. This term will come here. It will be 2 into 0.1. So 0.2 and 2 minus 1 w plus 6. If you put this is equal to 0, you will get the value w is equal to 30. Now, if you find the second derivative, which is this, the second derivative is equal to minus 0.2, which is less than 0. So it is a maxima. Since minus 0.2 is less than 0, it is a maxima at the critical water of 30 liters. So we found this critical value is 30. Now let us, and we know that the at the water supply of 30 liters, we are going to get a maximum for this function. So that is what we want. We want to maximize the yield. So we will substitute this 30 in this equation over here, and you will see that when you solve this equation, you will get 590 as the answer. And if you go back to the code, what you see for the parameter value of 30, you are finding the yield as 590, which is the maximum yield. So this is how the optimizer Optim is doing the optimization. We solved it manually also. We solved it using the code also. Okay. Now, let's try to do it for this problem. Now, if you see this problem, we have a more complex equation. 5 and, sorry, this is the equation over here. This is the equation over here. So we have two variables. So again, the amount of time we will take to solve this equation, because we have two variables, is going to be more. So it is in such situations that an optimizer is going to be of use to us. So I have manually solved this over here. Before we go into the optimization, let's look at how we can solve this manually. So here, manually, in order to do the first step, this is the function. I found out the first derivative of this equation. Maybe we can take a 5 minutes break. It's 7. I'll come. I'll return back in 5 minutes, and then we'll go into this more complex problem. I will be back exactly by 7:03. Let's like 3 minutes. 7:03. Okay. So let's resume. So first step, what I did over here for this problem, which is a researcher is wanting to maximize the plant growth by and the function is given by this one, where G is the growth, N is the nitrogen quantity, and P is the phosphorus quantity. Nitrogen available is 50 kg, phosphorus available is also 50 kg, but applying more than 10 kg of nitrogen is going to be bad for the growth. Secondly, applying less than 20 kg of phosphorus is not going to have any impact, but applying more than 40 kg will be toxic to the plant. So the constraints are these one. The decision variable is N and P, and the objective function is to maximize plant growth. So first we write the equation of plant growth, and then we find the first derivative of G with respect to N. Since we have two variables over here, we have to find the partial derivatives. That is derivative of this function with respect to N also, with respect to P also. So when you find the derivative of G with respect to N, this is going to be a constant. This is also going to be a constant. So dg by dn is going to be 5 minus a 0.2 n. And again, the next step is to equate it to 0. That time we'll get the value of n as 25, which is a critical point for n. Now, in order to find if this n value is giving us the maximum growth or the minimum growth, we will find the second derivative. And when we do the second derivative of this equation, which is the one we got of the first derivative, we will get the answer as minus 0.2. Now, since minus 0.2 is less than 0, it is going to be a maxima at this point. So, at this phosphorus quantity, at 25 kgs of phosphorus quantity, we are going to get a maximum growth. But then that is not just the criteria that we have. We have to look at the phosphorus quantity also. So similarly, again, we will go back in the second step. We'll go back to this equation, find the first derivative of this equation with respect to the phosphorus quantity. And then that is since it is P that is in the, we are deriving the equation we are finding the derivative with respect to the variable P. This value and this value is going to be a constant. So the first derivative is going to yield us this value, this equation. Now, when we equate it to 0 in this step, we get that P is equal to 50, which is the critical point for P. So, it means nothing but P is one value of the phosphorus, that is P kilograms of phosphorus. 15 kilograms of phosphorus is either going to give us the maximum yield, maximum growth, or the minimum growth. And to know whether it is maximum or minimum, we find the second derivative. And in the second derivative, here also we are getting minus 0.2, which is less than 0, as a result of which we understand that we are getting a maximum plant growth at a phosphorus of 15 kilogram. Now, next step, we go to the constraint. In the constraint, we know that uh, any quantity of phosphorus more than 25 kgs is toxic to the plant. So we have to have the phosphorus quantity within equal to or less than 10 kilograms. So N is 25 is not a possible solution or possible value that nitrogen can take. So we either take N at 0 or N at 10. We don't take N at 25 at the critical point, because by equation, yes, it can give a maximum growth, but in reality, this much quantity is going to be toxic to the plant. So we constrain the value of nitrogen to 10 kilogram, or we also check the value at 0 kilogram. So what we do is so that is one constraint that we have to apply. Similarly, we got 15 kilograms of phosphorus, but according to a constraint over here, you see 20, it should be between 20 and 40. So in order to do that, we will not use this low quantity of phosphorus, because there's no point in applying 15 kilogram. It is of no use to the plant. So we take the lower limit of this as 20 and upper limit of this is 40, and we don't find it at this critical point. So in the next step, what we do is we will find out what is the growth at a lower limit of nitrogen, which is 0, and a lower limit of phosphorus, which is 20. Then we will find out what is the growth at a lower limit of nitrogen and the uppermost limit of phosphorus. Third, we will also find out the growth value at the upper limit of nitrogen and lower limit of phosphorus. And here in the fourth step, upper limit of nitrogen and upper limit of phosphorus. Basically, we are substituting this constraint 0 to 10. We are finding what is the growth at 0 and 10 of nitrogen and 20 and 40 of phosphorus. So we get four solutions like this. So when we substitute for this first category over here, we solve it for this equation. This equation is 5n plus 3p minus 0.1 n square minus 0.1 p square. If when you put n value is equal to 0 and p value is equal to 20, we get the answer as 20. So the growth of the plant when the nitrogen, 0 nitrogen is given and 20 kilograms of phosphorus is given as 20. Similarly, we will do it for the second condition when nitrogen is equal to 0, phosphorus is equal to 40. What is going to be the growth? It is going to be a negative growth. So then this obviously is not a possible solution. Now for the third condition, we'll substitute 10 in place of N and 20 in place of phosphorus. And when we solve, we get that growth is equal to 60 when we use this condition. And for the fourth condition, that is when the phosphorus is equal to 10 and nitrogen is equal to 10 and phosphorus is equal to 40. When we substitute in this equation, we get the answer as 0. So there won't be any growth. So from all of these answers, the maximum value we are getting is this. Minimum value we are getting is this. So what we want to do, we want to get the maximum growth. So the optimal nitrogen content will be 10. Optimal phosphorus content will be 20 and the maximum growth is going to be 60. So for this condition, that is the upper condition, upper limit of nitrogen, lower limit of phosphorus, we are getting the maximum growth. So so the maximum quantity of nitrogen that can be provided is 10. After providing that, in the minimum quantity of phosphorus if we provide, we will get the maximum growth. For any other condition, the growth is going to be either 0 or less or negative. So this is the maximized growth, and these are the optimal parameters of N and P. Now, if you do, we will do the same thing in, if you do the same thing in R, I've done this here. Okay. So here what is happening is we are defining the function growth as a function of x. But then since there are two variables and since this optim function can only take one argument inside this bracket, it cannot take it cannot take n comma p like this. It can only take one argument. We name an argument called x where the first value, we're going to name an argument called x where the first value is going to be n and the second value is going to be p. So again, it is a vector. So this is the quantity of nitrogen and phosphorus that require to be provided in this equation, and this function will be written in this form, that is function of x where first index is nitrogen, second index is phosphorus. So n is equal to the first element of this vector and p is equal to the second element of this vector, and the equation is equal to 5 into n plus 3 into p minus 0.1 into n square minus 0.1 into p square. So this is going to be our function. Now we have upper and lower limit here. So our lower limit is 0 and that is 0 and 20. If you see here, the lower limit over here is 0 for nitrogen and 20 for phosphorus. So that is what we have here. The first value has to be the lower limit for nitrogen, and this value has to be the lower limit for phosphorus. Upper limit again 10 for phosphorus and 40 for phosphorus. You should be careful not to give both of the nitrogen value here and the phosphorus value here. We are giving the lower limits together and the upper limits together. And the initial value we'll give. Initial value is going to be something like 5 and 20. Now, if you see here, again, earlier, we were only using one variable x, not two variables. So, Optim, the default method that is used in Optim, which is that need and blend method, it is not capable of taking two variables and also. In order to consider multiple variables, we have to take into consideration another method called this LBFGSB. So here we put the initial value of the parameters, which is given by this variable initial values. The function is this growth function that we have defined. Method is going to be LBFGSB. The lower limit is going to be lower limit. Upper limit is going to be the upper limit that we have all defined over here. Control is going to be again FN scale of -1 because we want to maximize the growth. So let's run this function and see. Lower limit, upper limit, initial values, the maximum growth. And if you see the parameter value is 10 and 20. If you compare it to the problem that we solved right now, see, we found that the nitrogen and phosphorus at 10 and 20 gives the optimum value of 60. So whatever we did manually, we verified that even the optimizer code is doing the same thing. So this is how we do an optimization in R. Now what I have got over here is a few exercise for you to try. So just give me at least the objective function of this equation. A farmer is wanting to build, don't do it in the code. Just give me what is the objective function, what is the decision variables, and then I will help you with the code. Go on, just tell me what is the objective function in this problem. Okay, your answer is right, maximizing the area of the rectangular pen. Now, what is the decision variable over here? What can be the decision variable in here? Correct. The length and the width of the pen. Okay. Okay, let's see. Um, so the objective function defined here is to maximize the area, right? Variable is x. Now let's see how it is x. Now if you see, we know that perimeter is equal to 2 times length plus breadth. Now we know the perimeter. It is given 100 is equal to 2 times length plus breadth. Now 50 will be equal to length plus breadth. So length alone is equal to 50 minus b. So we get that we get this term L in terms of b. So now if we have the length also, we have the breadth also. So length, if we substitute in terms of b, we can get, say if this is b over here, 50 minus b, that is the length term into the breadth will give us the area. So this is the function. The function over here is area is equal to, sorry, so area is equal to length into breadth. We know that length is equal to 50 minus breadth because we had the perimeter value. So 50 minus b into b is the area. So this is the function that we can use in R. Now, objective function is to maximize A. And decision variable is, so we were able to reduce the decision variable to one variable, which is B. So that is how we simplify an equation. Now let us do the same thing in R. We are defining the function area, that is a function of x, and that function is defined by 50 minus x into x. This is the function. Now, our objective function is to maximize the area, and we use optim. The initial value of the parameter, I don't know, I'm just putting some value. Okay, Mayank gave us 25, so let's see if it is 25 itself. Function is equal to area. Now, another important thing, since it is maximizing, we have to use this control argument and provide the component fn scale is equal to -1. Now, let us see if we can get the optimal parameters of x. We maximize area. We see that for a breadth of, for the value of x equal to 25, the maximum area we'll get is 625. So the optimal value of the parameter x is equal to 25, and the and the maximum area we'll get is 625. So in this case itself, if we, so here uh, we get x is equal to 25, which is the breadth. Length will be equal to 50 minus 25, again equal to 25, which is the length, and 25 into 25 will be 625. So again, whatever, I don't know how Mayank did it, but if you're done during the derivative, it is correct. And if you do during the using the optimizer, we get this value. Now let's go to a second problem. Here a company is producing two products, X and Y, with a profit function P, which is a function of X and Y given by this equation. The company has resource constraints where X cannot exceed 20, Y must be between 10 and 30, and you have to find the values of X and Y. So either manually or using R, you need to give me the answer. I think I gave you a lot of example. I can give you the sample code also in the chat. Please use that and find it in R, or you can at least manually do it and find it so that you know about this concept of R. I'll give you this entire code now. Please do try. So, okay. Yeah, Mayank also, I think you must have got a grip of what objective function is, what decision variable is, what constraints are. So try using this code, or I have also given the manual way to solve this. Maybe I'll put that slide over here. This is how you solve it manually. That also I'll put here. This code also I'll give. I want you to take your time, no hurry. If you have any doubt, let me know, but do it. This code. This code also I'll give the. You can even use the same code, but change the values, change the function values, change the variable name, and then please post the code also. And if you're getting any error, let's discuss it now. Sorry. So at least copy paste this code, that is and write the code in R, copy paste it in the chat. You can direct message me and we'll see if it runs or not. So this is the equation, this is the function. So yes, tell me at least what is the objective function over here. What is going to be the objective function over here? What is the decision variable and what are the constraints? You can direct message me if before going into the code, or you take your time, do the code, at least do something. I'm expecting a response. So let me guess, did you use ChatGPT or something? Because your answer looks like the LaTeX code that is given there. Anyways, at least tell me what is the objective function. Anamta, are you trying? Okay, Mayank, can you paste the code here? At least the function. How did you give the function? Direct message me. Okay, Anamta left because I think she wasn't getting, or probably some. No problem, no problem. Are you able to do something? No, no, Mayank, I am asking you to do this problem, not the growth problem. This problem I have given over here on the screen. This is the equation for that growth problem which I had done earlier. Okay. Okay, let me move to the solution. So in order to do this, first what we'll do is we'll define the function. The function is profit, which is a function of, say, some variable x, and the function is given by not variable x, say let's make it a, and the function is given by this formula here, 5 into x plus 4 into y minus minus 0.1 into x square minus 0.1 into y square. So this is our function. Now x is equal to the first vector of a, and y is equal to, let's write equal to here so it becomes more, second vector of this variable or the set of variable a, and the function that you want, you will write it in return. Okay. So now we define the function. Now our objective function is to maximize the profit. And if we are using Optim, first we need to give the parameter value of x and y, initial value. So that can be like say 10, 10. Then we give the function which is profit. Now we have some constraints, which is basically x should be between 0 and 20 and y should be between 10 and 30. So let's put the constraints over here. Let's do the lower limit is equal to c 0 for x, and for y it is 10, and upper limit is c 20 for x and 30 for y. So let's put this as 5 and this is 10. Function is profit. Lower is equal to lower limit. Upper is equal to upper limit. Now control is equal to a list with fn scale, the function scale equal to -1. Now let's run this code. We ran the function, there is no error. The lower limit, the upper limit, and with that function, it's just a warning, maximize profit. We get that for the parameter value x and y 20 and 20, whatever is the profit will be 100. So this is the maximum profit you can get with an optimal value of 20 and 20 for x and y. Now this is how you will use the optim function for now. Suppose you want to define many equations over here, then I'll explain in the next class, where there is a lot of equations involved. So ultimately you need to, or you're doing a curve fitting. Then in such cases, we will have to define a function where the error between the predicted value and the observed value is going to be the least, and subsequently the lower limit and upper limit and all will have to vary accordingly. So that I'll be taking in the next class. And again, here, if you want to access this, now we have the maximum profit as the objective function. So maximum profit is in the form of a list. If you see here, type of maximum underscore uh, maximize profit. It's my code running import necessary libraries and numpys. Define the profit function x and y 5x. Okay. Negative profit function for minimize lower limit is equal to, okay, this is Python. Okay. NP array run optimization maximize result is equal to optimize dot minimize. You have to maximize it. Okay, minimizing the negative profit. Okay. Negative profit initial values. This is the Python code, so you will have to put it inside Python and figure it out. Since I'm using R and I'm not very proficient, I mean, I can run it, but I'm not very proficient with this code that you get for Python. Try getting a code for R, same way you've got this. So here, maximize profit is a list. So you can get the values of the parameter you run, you will get the value of this one. And then maximize profit, $sign. If you want the value, you get, this is the profit value that you get, and this is the value of x and y. Now, there are so many other things here. If you see count over here, gradient convergence, message convergence norm. What is this? Norm of projected gradient P. So many stuffs which even doesn't make sense to me. So yeah. So this is basically how you'll do simple optimization in R. So yeah, that will be for today's class. If you have any doubt, you can let me know. Otherwise, you're free to exit the session. Do practice R. It is going to be a lot of use to you for data analysis. So yes, we'll see in the next class with optimizing using BioCro code, how to optimize parameters of our photosynthesis. And it will be something like this only, except that the function, the equation that we will be defining will be a bit different. So yeah, that will be for today's class. Thank you for attending the class, and good night. Yeah, Mayank, you can use R. I mean, you can use Python also. Why I'm focusing on R is because BioCro is mostly on R, so that is why I'm focusing on the R program. You can, for optimization, you can use any code which you're familiar with. You can use Python or anything. So the reason why I'm doing this optimization part is to introduce you into optimizing parameters of BioCrew. So that is why I'm more on R.
Ma'am, but sometimes R is more complicated and confusing rather
Yeah,
than Python.
I understand, but again, for running BioCrew, you need R. So I think
Okay, ma'am. Because it is very useful for our research purposes also in fourth year in BS Honors.
yeah,
Thank
sure.
you.
Okay, thank you.
Ma'am, can you please suggest me a way to practicing all these question on R for easy way to going on and medium and then hard for R.
Um, I mean, there R is, I mean, there are plenty of resources. I think I can share you some. I'll put it in the group. There are some resources where you can study R easily. Uh, and I mean, as far as you guys are concerned, you have plenty of resources in the internet. You can either do that or you can join a course. There are plenty of courses available for 600, 700 rupees where they will introduce you to the basics of R. So you can do that.
Okay, ma'am. Maybe in my BSc course, research methodology is also included in fourth year. Maybe at that time, I will taught in my college
Okay,
about R.
okay, okay. Whatever
Thank you, ma'am.
works. Okay, thank you.
ठीक है. Good evening, ma'am.